Well, this morning it gives me great pleasure to introduce our speaker, Dr. Kendall Melville. Ken is a professor of oceanography at Scripps in the Physical Oceanography Research Division. In addition to his role as a faculty member and a researcher here, Ken has a long history of service to SIO, including serving as chair of the graduate department for 5 years, as well as deputy director for education. And Ken came to SIO after a decade as a professor at the Massachusetts Institute of Technology. And among numerous prestigious awards, Ken is a fellow of the Acoustical Society of America, and his contributions to the field of physical oceanography are many. In fact, he's supervised over 25 graduate students, and he's authored or co-authored over 100 published research papers. And Ken came to oceanography through the study of mathematics, aeronautics, and astronautics. And his research interests therefore span a very wide range of science and engineering disciplines, but they're focused primarily on fluid mechanics and its application in oceanography and air-sea interactions. And today Ken is going to speak on waves in and on the ocean.
Well, you've already heard the title of my talk today, and what I would hope is that by the time I've finished and you go away from here, you will understand that as well as having waves on the surface of the ocean, as you see here, that there are waves in the interior of the ocean, and for some of the things that affect us on almost a daily basis. In some cases, the internal waves, especially in Southern California, may be just as important as these surface waves. If you look out over the ocean this morning, it's very calm. We have almost a Santa Ana condition, or we have a Santa Ana condition, and the waves near the shore are very small, and it's difficult to imagine that the ocean can become like this. This photograph was taken in a storm in the North Atlantic from the research vessel Noor when the winds were around 55 knots, gusting up to about 60 knots, and the waves were about 40 to 50 foot high when the vessel was in the troughs of the waves. Standing on the bridge, the crests were about eye level, and the bridge was at 44 feet. So this was quite a storm. This is a very well-known storm, sometimes called the perfect storm. This is the storm from Halloween 1991, about which the book The Perfect Storm was written, about the loss of the Andrea Gale with 6 sailors aboard, or 6 fishermen aboard. And in this storm, you see the typical anti-clockwise circulation of the low-pressure system over the North Atlantic. The winds here, the maximum winds here are up to 65 knots with waves greater than 40 feet. It's interesting to note that the fishing fleets that left from New England had enormous losses in weather like this during their history, peaking in the late 19th century. The port of Gloucester was losing approximately 100 fishermen a year at sea. So you can imagine every week must have been a pretty grim experience during those times. For those of us who come from down under, this was our perfect storm, if you wish. This was a storm during the 1998 Sydney-Hobart yacht race. This is one of the classic yacht races. And it's a 630-mile run from Sydney down to Hobart. And this is a film clip of the weather from one of the weather satellites during that time. Australia is not moving because of seismic activity. It's moving because the satellite is moving, and so the coastline moves. But what you'll notice here is that approximately halfway between Sydney and Hobart, this storm really twists up, and the rotation now is clockwise. We're in the southern hemisphere, so the rotation around the low, and you see the low spinning up there, looks very similar to the Halloween storm, except it's in the southern hemisphere. In that yacht race, 115 yachts started, only 44 finished. 12 boats were abandoned or sank. 6 sailors died, and 55 sailors were rescued. The winds there were in the range of 55 to 70 knots, with wave heights up to 15 meters or 50 feet. So quite comparable to the Halloween storm. Well, what does all this have to do with the title? We know that storms like that generate very large waves, and this looks like a technical slide, and I promise it's about the only technical slide you'll see this morning, but there are just a couple of points on here that I'd like you to remember as I talk. What you see at the top here is I have a little cartoon of wind blowing offshore, as we have in a Santa Ana condition like the present one, where the wind blows off the land out over the ocean. And the distance out over the ocean we call the fetch. This is the distance that the wind blows. And as the wind blows offshore, the waves increase in amplitude and they increase in length. And if you look at the little inset down the bottom here, I've shown just a few of the technical terms we use. For example, the distance between the crests, adjacent crests of the waves, we call the wave length. The distance between the crests of the waves and a trough, we call the wave height. The speed of the wave, either wave speed or technically we call it the phase speed. This is the speed at which the crests move, and here denoted by V. Now, if you've ever been down in the surf here, you'll notice that as you're floating in the water, as the unbroken waves come by, you undergo simple oscillation, and you don't go anywhere. I mean, you just oscillate around in the same place. Now, this is one of the attributes of waves, is that they can transfer energy and momentum without significantly transferring mass. In this case, when you're down at the beach, you're the mass. However, when a breaking wave comes along, you'll notice that you get moved very rapidly forward, and this is the art of surfing, being able to choose the right time to catch the wave. And you've done it both voluntarily and involuntarily in the surf, I'm sure. And you know that when the wave breaks, you move forward very rapidly. Well, this is just a reflection of what we know about the orbital motion, the motion of the water in the waves, which I've denoted here as U. And there's another important parameter, and that's the steepness of the waves. And we describe that as essentially the ratio of the height of the waves to the length of the waves. So the longer the waves are for the same height, they're less steep. The shorter the waves are, they're more steep for the same height. And just a simple technical fact that the motion of the water in the wave is approximately proportional to the wave slope times the speed at which the waves move. So if this slope is much less than 1, as it normally is, then the speed at which the water moves, or the speed at which you move when you're bobbing around in the surf, is typically very much less than the speed at which the waves move. Unless, and this is really the most important part of the talk as far as surface waves are concerned, that when the waves break, the speed at which the water moves is approximately the same as the speed at which the waves move. And here's a little example of the speed at which waves move for a wave length, the distance between the crests of 60 meters, a little bit more than half a football field. The wave speed is 10 meters a second, or 20 knots, or 23 miles an hour. So a significant speed. One other point, we call these waves surface gravity waves because gravity is the restoring force. And there's an analogy with a spring. I stole my daughter's slinky. And in the case of the spring here, the restoring force is the spring itself. We characterize that by the spring constant. And a typical simple spring mass system has a mass at the bottom and the spring, and I let the spring go and it oscillates. In the case of the gravity waves at the ocean surface, the restoring force is gravity. If I displace the surface by either moving it down or pushing it up and let it go, it will try to go back to an equilibrium position, which is a flat ocean. And in doing that, it oscillates. Now, taking those simple ideas and taking some rather complicated equations and taking observations from both satellites, and here's an example of winds at the ocean surface measured by a satellite called a scatterometer. This scatters radio waves off the ocean surface, and by looking at the characteristics of the waves that are reflected back, you can get information about the wind speed or the roughness of the ocean surface, which is related to the wind speed over the ocean. And this was from January 2003, and you can see storms in the North Pacific, North Atlantic, and in the Southern Ocean. A lot of action going on here. The other input to the observations, I don't know whether you can see this, there's a buoy, a surface buoy here, ships. There is a network of observations from surface buoys and ships. And so the observations from space, the observations from the ocean surface are melded together and go into a computer model of the surface wave field. And in this model we have wind forcing, the sort of wind forcing I just spoke about. As the wind blows, the waves grow. There are interactions between waves of different wavelengths. There are interactions between waves and currents, and this is an important point that I'll mention in a minute. And as waves propagate from the deep ocean into the coast, the water gets shallower, and that has an effect on the waves. They're said to refract, just as light refracts through a prism. And we also have the important process of wave breaking. Remember, it's this process that shifts the velocity in the water from being relatively small to being quite large. Now, this is the sort of information that you can get from the web, which is the output of one of these models. This is a prediction, a 36-hour forecast taken from midnight yesterday morning, Greenwich Mean Time, 36 hours out. And that was the closest I could come to the present time. And this shows the wave height. The scale is on the bottom here, going up to 40 feet. We call this the significant wave height. That's just a technical term. The maximum waves that you will typically find are up to almost twice this, 1.8 times this value. And the arrows here show the wave directions. And if you look closely at this, you'll see that there's these wave height predictions closely follow the wind patterns. And you'll see that there's a front moving down the coast here, and I think they're predicting rain sometime on the weekend. And ahead of this front, we have waves propagating down the coast. This is the common experience here, that when there's a distant storm, either in the southern hemisphere in our summer, or in the Gulf of Alaska in winter, the waves that are generated from those storms, the swell arrives first because they're the longer waves and they travel faster. So this sort of information is available on the web. This is output from the US Fleet Numerical Meteorology and Oceanography Center. That's one of the major prediction centers for ocean waves. The other major center is the European Center for Medium Range Weather Forecasting, ECMWF, which is based in Reading, England, and they put out similar forecasts. In fact, the European Center for the last 5 years has used wave prediction models to couple into its predictions of the weather, because they've found that in order to improve their prediction of weather and climate, they have to take into account the wave field at the ocean surface. Now, there's a rather popular subject for the last few years has been the issue of rogue waves. While the models, ocean wave models, can predict waves globally now with reasonable precision, you still have examples of situations like this. The headline, "Rogue Wave Smashes the Queen Elizabeth II." And let me just read this red script in the bottom here. At 0410, the rogue wave was sighted right ahead, looming out of the darkness from 220 degrees. It looked as though the ship was heading straight for the White Cliffs of Dover. This is an English vessel. It broke with tremendous force over the bow. An incredible shudder went through the ship. There seemed to be two waves in succession as the ship fell into the hole behind the first one. The second wave of 28 to 29 meters, 93 to 97 feet, whilst braking, crashed over the foredeck, carrying away the forward whistle mast. Rather a dramatic event, which proves that it's not just the people who go down to the sea each day to earn their living that can experience this sort of thing, but also the well-to-do passengers of the QE2. This is an example of a somewhat smaller, quote-unquote, rogue wave. This is from, I believe, in the mid-80s, February 1986, the SS Spray that previously was named the Gulf Spray, an oil tanker in the Gulf Stream of Charleston. And according to the report from somebody on the bridge, they said that this wave coming up here, and you can see it just beginning to break along the crest. This wave broke over the heads of the crew on the bridge at a height of 56 feet above sea level. And they go on to recount the damage to the foredeck here, including this mast being bent back about 20 degrees and equipment being stripped off the foredeck. So these waves, and this wave occurred in relatively calm conditions. Now, there are certain locations around the world where these sorts of waves tend to be more prevalent, and I've circled them here. You've already seen an example of the storm off the southeast coast of Australia, and this is the East Australia Current. This is the Kuroshio, the Gulf Stream, the Agulhas Current off the southeast coast of Africa, and there have also been important losses of vessels off the coast of Norway. Norway has a large fishing fleet. And the common thing about these areas is that they're all in situations where waves generated by storms at high latitudes, that is closer to the poles, can propagate against these currents. So waves coming from the Southern Ocean can propagate against the East Australia Current, against the Agulhas Current. Storms in the North Atlantic oppose the Gulf Stream, the North Pacific, the Kuroshio, and similarly for the currents off Norway. This is an example of wave-current interaction, that waves become steep and break on entering opposing currents. And if my slinky will work for me again, if you imagine waves moving to the left and consider my slinky as a wave, then when you get an opposing current, that will tend to concertina the waves. They become steeper and shorter, and we know as they become steeper, they tend to break. And remember, when they break, the velocity goes up a great deal. And this is what does damage to these vessels. There were many examples during the time of large oil shipments around the coast of Africa from the Middle East to Europe, supertankers that were too large to go through the Suez Canal. A number of them struck trouble in this region here, either being lost. Some of them actually had their backs broken in large waves as they tried to round the southern tip of Africa. Now, oceanographers have a lot more interest in surface waves than just what I've been telling you about large waves and the effect of braking on vessels. The surface layers of the ocean are an important region for air-sea interaction, the interaction between the atmosphere and the ocean. And we know that the wind blowing over the ocean generates surface waves. There is a lot of heat transfer due to solar radiation. In fact, 80% of the incident solar radiation is absorbed in the first 10 meters. There's an important point that the first 2.5 meters of the water column has the same heat capacity as all the dry atmosphere above. That is, it takes as much heat to raise the temperature of those 2.5 meters 1 degree as it would take to raise the temperature of the whole atmosphere 1 degree. So the ocean has an incredible ability to store heat. The other important thing is that the pressure, the hydrostatic pressure, doubles in the first 10 meters. Goes from atmospheric pressure to twice atmospheric pressure. And this is important for the process of gas transfer. When waves break, as you'll see in a minute, they entrain air and bubbles. And as the bubbles get pushed down to depth by the currents associated with braking. As the pressure increases as they go down, and the bubbles get squeezed into solution. So this is an important process for gas transfer between the atmosphere and the ocean, and we know how important that is for issues like greenhouse gases and the sequestration of greenhouse gases in the ocean. So again, for these sorts of reasons, wave breaking is an important process at the ocean surface. Now, I've spent a significant fraction of time in the last 20 years or so looking at the process of wave breaking, starting in the lab and moving out into the field. In work we did in the 1980s in the lab, we were able to show that using modern laboratory techniques, that you could do very well-controlled experiments on measuring how much momentum went from waves into currents due to braking. And this is an important pathway because the wind generates waves, and the waves give up their momentum to currents. So when we talk about wind-generated currents in the ocean, what we're really talking about is the process of momentum going from the wind to the waves to the currents, and the most important process by which the waves give up their momentum to currents is through braking. So we were able to do some work in the lab on that. However, while you can do controlled experiments in the laboratory, you can't measure the statistics of the waves or braking statistics in the laboratory because you're not really generating a realistic ocean wave field. So for example, if you were interested in predicting the probability of a ship meeting a rogue wave or the probability of wave breaking in the ocean, you can't do that in the lab. You have to go out to the field. And in recent years, we've been working on ways of using modern imaging techniques to do that in the field from aircraft. There's another important point about work on air-sea interaction and surface waves in recent years, and that is the move to do these measurements in extreme environments. The damage done by hurricanes around the world is significant on an annual basis, and we're particularly concerned about being able to predict the strength and track of hurricanes, especially as they approach landfall. And recently, this was just last month in Nature, Powell, Vickery, and Reinhold showed that extrapolating from measurements at lower wind speeds and smaller seas up to hurricane force winds doesn't work. That we can't simply extrapolate our measurements from more benign conditions to hurricanes because the physics changes, the processes change. And so this is a very important piece of work that is going to motivate more work into doing hurricane research, the air-sea interaction of hurricane research. This is an example of wave breaking in the laboratory. Just to show you some of the things I mentioned earlier, you can see the entrainment of air. This is slowed down significantly. This happens in the twinkle of an eye, about 1 second, and it's slowed down significantly. Let me just do that one more time. You can see the spray being thrown up, you can see the air being entrained, and there's a lot of turbulence and mixing. So if the surface layer here was warmer, the turbulence from this breaking would mix that heat down further into the ocean. In 1999, we tried to take some of the imaging skills that we have from our work in the laboratory and take it out to the field. We installed video equipment, a camera here, an infrared camera, and this is an inertial motion package that measures where we are in space and our orientation in space. We also used GPS and flew this package on this pod under a Long Easy aircraft flown by a colleague from NOAA. This is in fact the Long Easy taking off from Kill Devil Hills. Scripps is having its centennial celebration this year, but so is the first flight centennial this year. In December 1903, the Wright brothers first had controlled flight from Kill Devil Hills near Kitty Hawk off the coast of North Carolina, and we in fact flew from that airfield within the shadow of the memorial to that flight. We flew out over the Atlantic. When I say we, I'm using it figuratively. This aircraft had room for one pilot, Tim Crawford, who unfortunately died last year in an accident. But this is the sort of imagery we can take. These are still images of the ocean at different wind speeds, going from about 8 meters a second, 10 meters a second, up to 14 meters a second. You'll notice that the incidence of breaking, the fraction of the surface covered by whitecaps increases as the wind speed increases. And what our aim was to actually, by taking sequential images of the ocean surface and knowing very accurately where we were from the instrumentation on board the aircraft and GPS, we were able to correlate sequential images and measure the speed of these whitecaps. And this is just an image of a processed whitecap showing, these are in fact little arrows showing the magnitude and direction of the velocity associated with that whitecap. And come back to the point, remember that I said earlier on in the talk, the important thing about braking is that when the waves break, the speed of the breaking wave is comparable to the speed at which the wave moves, which is much larger than it normally is. And this is what does the damage to ships. This is what mixes the surface waters, so it's important for the heat transfer. This is what mixes the gas, so it's important for the gas transfer. So for all of these processes, it's important to know how fast these breakers travel. So we were able to measure the statistics of these processes in the ocean for the first time. Last year, we extended our work to work with in the Hurricane program. This is one of the NOAA Hurricane Hunter aircraft, a P-3. These aircraft used to be used for submarine patrol. They have long range, long endurance in the air, and they go out for about 10-hour missions, flying into the eyes of hurricanes. This was Hurricane Isidore, September last year. We had our imaging equipment and other equipment on board an aircraft just like this, and flew these tracks as Hurricane Isidore entered the Gulf of Mexico. This is just a map. This is South Florida, Cuba, the Yucatan Peninsula, and this is just plots of whitecap coverage plotted vertically here, showing how the whitecap coverage in the hurricane varied, and so the statistics of wave breaking in the hurricane varied. Next year, we plan to extend our work down into Mexico, the Gulf of Tehuantepec. This is work that has just been funded by the National Science Foundation. We're in the process of trying to get access to a C-130 aircraft now to carry our instrumentation. And this area here is known for what are called gap winds. This is a topographic map of the Mexican peninsula here, and at various positions here and here, for example, there are gaps in the mountains where winds can blow from the Gulf of Mexico out over the Pacific. And this one here in particular, in the, adjacent to the Gulf of Tehuantepec, gives rise to these very strong winds. This is an example of wind maps, and you can just see the air streaming out here from the Gulf of Mexico out over the Pacific. The winds here can reach 40 knots, 50 knots, and extend out over the Pacific for distances of 500 to 600 kilometers or more. So we're planning to fly this aircraft using imaging instrumentation and other instrumentation to measure the waves, to measure the atmospheric boundary layer, how the wind evolves, and we're going to drop things out of the aircraft to measure the atmosphere and to measure the ocean. Now let me turn to internal waves in the ocean. I said earlier that much of the solar radiation from the sun goes to warming the surface layers of the ocean. And here is a simple cartoon plot of the ocean going from 0 down to about 5 kilometers. And the effect of this heating is to warm the surface layers here, developing a seasonal thermocline that fluctuates between summer and winter, and a so-called permanent thermocline which is reasonably unscathed by the seasonal fluctuations. So the ocean has a significant temperature gradients, especially near the surface, and these warm surface waters are less dense. And just a 10 degrees centigrade increase in temperature reduces the density of the water by 1/1000th. Now you may think that that's not a lot, but it has important consequences. So if you consider a surface of constant temperature or an isotherm, then if you displace that surface, then it too will be restored by gravity, just as the surface between the atmosphere and the ocean is restored by gravity. And this leads to internal gravity waves. So let me take my slinky again, and now I have to step away from the podium. I'm now going to simulate an internal wave, and I can do that with the same spring by effectively making it longer so I have more mass on the end, and that reduces its frequency. So let me show you. This is what I did for surfboard. This is what I did for surface waves. I displace it, and it oscillates pretty quickly. If I lengthen the spring, so I'm effectively putting a bigger mass on the bottom, this slows the frequency down. You see it's much slower. It's the same thing with internal waves in the ocean. Here, we've effectively reduced gravity by reducing the density difference across the interface. The density of water is about 800 times that of air. For the internal waves, we're just changing the density by a small amount, and that effectively reduces gravity. Indeed, we call it reduced gravity. And the effect of that is to lower the frequency of waves in the interior of the ocean. These are images taken from a paper by Osborne and Birch. This was in fact a cover photograph from Science magazine at that time. And this is what we call a sun glitter photograph from the Soyuz spacecraft over the Andaman Sea. And the Andaman Sea butts up against Myanmar, or formerly Burma, and the Malay Peninsula in the tropics. And what was of interest to the Soyuz astronauts or cosmonauts were these streaks on the surface. Now, at about this time in the mid-70s, Osborne worked for Exxon, and they were doing exploration in the Andaman Sea from a drill ship. So they had a dynamically positioned vessel at the surface with risers going down to the bottom of the ocean. And what they were finding was, on a regular tidal cycle, the ship was being whipped around on the end of the drill string. And so they had to investigate, because the cost of having these things break and having to have them repaired would be quite significant. So they actually did some research, and they discovered these images from the Soyuz spacecraft. They went in and took some measurements, and this is what they saw from the vessel, that as time went on, the time goes A, B, C, D, E, F, G, H, etc. You could actually see lines of breaking waves approaching you. The sea got rougher, and then it got smoother again. Now, if you look out here on many days, you will see lines of smooth and rough water, and you'll say, well, that's interesting. But if you took time-lapse photography, or you were patient enough to sit there and look at the same streaks for a while, you would see them gently approaching shore. These are the surface signatures of internal waves, and the currents associated with the internal waves interacting with the waves at the surface can cause them to break. Just as in those areas around the world where you have waves from high latitude storms approaching the western boundary currents, causes those waves to break. So the same physical process, but on a much smaller scale, is what permits you to see these variations in the sun glitter pattern at the ocean surface. Now, since that time, the measurements of from space have become more quantitative, and in 1996, Ray and Mitchum actually used Topex Poseidon altimeter data. This is a spacecraft that sends a radio signal down to the ocean surface, measures the time it takes to get there and come back, and from that it can measure the height of the ocean surface. And these are tracks of this satellite, and this is the Hawaiian Ridge, and you can see that there are oscillations here surface waves about 5 to 10 centimeters high that are in fact the signatures of the internal tide. So similar to the glitter signatures you saw, there's a signature in the displacement of the surface, and these are in fact internal tides caused by tidal flow, the surface tides flowing over the Hawaiian Ridge. In the 1960s, John Miles at Scripps did some work on a similar problem. This is a stratified flow, or flow of varying density, over model of a mountain range. And you can see that these lines, which are lines of constant temperature or lines of constant density, fluctuate as the wind blows over this mountain range, and we call these lee waves. And here they're shown for increasing wind speed over the mountain. The same sort of thing happens with currents flowing over the Hawaiian Ridge. These are like undersea mountain ranges here, and as the surface tides flow over the ridge, then they generate waves like this that can then propagate away from Hawaii. And that's what the spacecraft was measuring. Since that time, there's been a large field experiment headed up by Rob Pinkel and Dan Rudnick here at Scripps to look at the generation of these tides, not just from space but in the water. And this yellow cross here between Kauai and Oahu is where these measurements were made. And this is the depth from 1150 meters down to 1500 meters, and this is time. And these are isotherms, lines of constant temperature. You can see that they're depressed by several hundred meters, up again and down again, over about 12 hours, the tidal cycle. This led to headlines in various places around the world, and I think Dan dramatized the fact about internal waves of 1,000 feet high propagating away from Hawaii. They are dramatic, but they move very slowly. Now, why should you worry about that? A similar thing happens here just off Mission Beach. These are data from Jim Lerzak, a student at Scripps. He put in moorings off Mission Beach that measured temperature and currents, and these are samples of the temperature records going from deeper water into shallower water. And the color code here is 18 degrees centigrade, 12 degrees centigrade. And you get these warm pulses of water coming in off Mission Beach with the tide. So the same sort of thing that is seen in Hawaii is happening off the coast here on a somewhat smaller scale. Now, why should you worry about these things? This is an example of some data off the coast of Oregon by Jim Moon at Oregon State University. One of his co-authors was Larry Army here from Scripps, showing this is an acoustic image of scattering from one of these internal waves. Here the scale is 20 meters deep, 40 meters deep, and you can see that there are large fluctuations and mixing going on here, similar in some respects to the mixing that you saw in the surface wave that I showed you in the laboratory. Here you can see these layers winding up on themselves. It looks very similar to breaking at the ocean surface. Now, this is a little simulation I got from Clint Weinert at Scripps. This is the internal surf. Imagine that this is the surface of the ocean, and this is the beach, and this is cooler water below. The red stands for warmer water, the blue for cooler water. And imagine that you're standing at the beach here, and you've got your toes down here, and your chest is up here. Then what you'll experience is that your toes might feel cool while your chest feels relatively warm. And any of you who have been to the beach here in late summer have probably experienced that. You'll be standing in the surf and you'll be wondering, why are my toes cold when the rest of me feels warm? And this is what's happening, that the internal tide that we saw off Mission Beach, which also occurs off here, can actually flow up onto the beach. And there are similar temperature records off the Scripps Pier. Now, there's an important practical problem, and this is really the last piece of my talk. Major cities, major coastal cities around the world all have sewage outfalls in the ocean. I think that's a fair statement. And so the idea is to treat the sewage to some extent and put a pipe down along the bottom and send it out a few miles into water maybe of 30 or 90 meters depth, and then pump it into the ocean. Now the sewage is typically less dense than the ocean water into which it's being pumped, so it rises up to some level where it matches the density of the water around it, and then it just spreads out like a cloud in the atmosphere. So then the question is, what happens? The idea of these diffusers is to try to mix the sewage, to dilute it. Sorry, the treated sewage, to dilute it. But the question is, what is the role of these internal waves that we saw in the coastal regions on mixing that sewage? So in order to understand that, and in order to understand how this is transported in the coastal ocean, we have to know what the currents are. And this is where the surface waves become important again. That we can actually use coastal radars or sending radio waves out over the ocean that are scattered back from the surface waves, and we can measure the Doppler shift due to those surface waves. Just like the train whistle approaching you and receding away from you. As it's approaching you, the frequency goes up. As it's receding away, the frequency goes down. You can do the same thing by scattering radio waves off the ocean surface, and the receding waves will be at a lower frequency, and the advancing waves will be at a higher frequency. Now we know the speed at which the waves move at. We can predict that well in the absence of currents. But if there are currents, then these peaks that you saw in the previous slide are shifted away a little bit from the frequency they would have if there was no current. And that small shift in frequency actually tells us what the currents are. So if you have radio transmitters and receivers at different locations around the coast, and this is work by a colleague of mine, Eric Terrell, a former student, who is in the process now of setting up a coastal observing system with these CODAR systems, coastal radar systems, at Point Loma, down at the border, out on the Coronado Islands. By having several of these stations, you can actually measure various components of the current and produce maps like this. This is an example taken on the 25th of February this year during a contamination event in Imperial Beach, where this radar system that actually uses the scattering of radio waves from the surface waves to infer the surface currents actually gives you maps of surface currents. And here you can see an eddy just off the coast of South Bay. This is the border area here, the Tijuana River. And at this time, there was a contamination event recorded at Imperial Beach. And you can see that the current is coming northwards from the Tijuana River area up towards Imperial Beach. This is another example. Now, the vectors, or these little arrows, show the currents, and the color bar here is total suspended matter in the water column for an Indian satellite that gives you coastal color, or gives you color maps at 300 meters resolution. And this is the plume coming out of the border area. And you can see on this inset here that the direction in which the plume moves is well tracked by the surface currents. So I hope that in this rather rapid move through surface and internal waves, I've given you some idea of the issues that confront us as we try to better understand the processes occurring at the ocean surface and in the interior of the ocean. I hope I've also convinced you that these processes are not so remote from our daily lives, especially the latter part on internal waves, where we now understand that these internal waves can play an important role in transport in the coastal region and mixing in the coastal region. And that's something that affects us. It's something that perhaps underlies beaches needing to be closed. So these are important aspects, not just of science, not just for the community, but for us individually. Thank you very much. Seamen are famous for telling tall stories, as we see. I don't know the truth of those rumors. I suspect that what happens is that particular areas of the ocean, as I tried to explain to you, can become rather dangerous. And up until the time we understand why they're dangerous, folklore and rumor tend to propel explanations for those disappearances or for those losses. For example, the Norwegian fishing fleet were losing vessels without any trace. Vessels were being lost without even enough time to get a mayday call out. The implication of that was that they were capsizing and breaking waves, and the Norwegians spent a lot of time in the 70s and 80s trying to investigate that problem, and also looking at the stability and the effectiveness of their fishing vessels in those sorts of conditions.
I think they had the same sort of thing up the Alaska waters with the crabbing vessel disappearing without being able to send
quite possibly. Yeah. In fact, the National Research Council did a study in 1991 of fishing fleet safety and concluded that fishing was in fact the most dangerous job in the U.S. On a per capita basis. Oh, they do mix, but they often don't mix completely, or it takes some time for things to mix completely. So until they do, whether they're mixed by internal waves or mixed by the surf, until it is well mixed, then you can feel that temperature difference and measure it.
And what was the depth of the warm layer coming in on the beach?
Oh, that was just a cartoon, but I know from my experience that I've experienced this. The cold toes, warm chest down in the surf here, and I'm about 2 meters tall, so that's roughly the scale of it. Well, one of the problems with matching the internal tide to the surface tide is that the stratification of the water column changes. The surface tides are extremely predictable because they're astronomical tides tied to the motion of the Earth, the Sun, and the Moon. So they're extremely predictable. The internal tides have been notoriously less predictable because the stratification on which they are propagating changes. So the speed of the waves change. So it's much less predictable. Well, in that case, the typical average ocean depth is around 4 kilometers, so 4,000 meters, and so that's about 14,000 feet. So still the ocean is much deeper than that in its deepest places.
Thank you very much.
Thank you.